Hello everyone, welcome back to Networks class. Last time in class we looked at Dijkstra's algorithm, which was our first algorithm for solving shortest paths. And we saw that Dijkstra's algorithm works much faster than a linear program for solving shortest paths. But pretty soon on a homework assignment you'll show me that Dijkstra's algorithm actually only works when the graph has positive edge lengths. So if it has any edge lengths that are negative, Dijkstra's algorithm isn't going to work, or probably is not going to work. And so today we're going to look at how we can go about solving shortest paths when we have some negative edge lengths. And we're really going to come at this from a particular application. So the application that we'll look at is something called PERT CPM, and PERT stands for Program Evaluation and Review Technique, and CPM stands for Critical Path Method. So these aren't particularly informative names, but you'll see a little bit, at least where Critical Path Method comes from. And really there's two parts of lecture today. So first is this application of PERT CPM, and the second is this new algorithm for shortest paths that we're going to learn called the DAG shortest path algorithm that works specifically on directed acyclic graphs even when some of the edges happen to have negative edge lengths. So let's get started by looking at this application for PERT CPM. So the basic idea here is, so this is PERT CPM. The basic idea is that we're given a set of tasks with completion times for each, and a list of prerequisites. For each task. So here's an example of the kind of data that we might get. So we might have some different tasks, maybe D, C, E, and A, and B. And then each of these tasks has some kind of completion length. So for example, task D might take us 2 days to complete, task C takes 1 day, task E takes 3, A takes 1, and B takes 3. And then they might have some prerequisites. So for example, before we can start doing task D, we have to complete tasks A and C. Maybe we have to complete tasks A and B before doing task C. Maybe just task C before doing task E. And let's say tasks A and B have no prerequisites. So we've already kind of seen this once before where we had a list of tasks and a list of prerequisites. And we discussed it basically when we were looking at topological sort. So with a topological sort, we can get a listing of the tasks in an order which allows us to complete them. So kind of a topological sort here would look something like this, maybe B, A, C, D, and E. And then the prerequisites would be, for example, D has a prerequisite of A and C. So A and C are prerequisites to D. C has a prerequisite of A and B. And E has a prerequisite of C. And that's pretty much all of the prerequisites that we have. And so this topological sort gives us an ordering, but the question that we'd like to ask is not so much what the order in which to complete the tasks in, but how quickly can we complete all the tasks. So that's the basic question that we're going to try to answer. And answering this question is somewhat subtle because you can't just add up all the lengths of these tasks because we might be able to process a couple of tasks in parallel. So for example, we could work on task B and on task A at the same time. So we have to be a little bit more careful. So let's think about how we can go about answering this question. How quickly can we complete all the tasks? So certainly we can complete all of the tasks in an infinite amount of time. So imagine that we have this this kind of bar. So right now it's at infinity. And it's true that we can complete all the tasks with an infinite amount of time. And what we're going to do is we're just going to move this bar up. So as I'm moving this bar up, what could stop me from completing the task earlier? So suppose that I could complete everything in 21 days, but I can't complete everything in 20 days. So what's the thing that stops me from saying that I can complete it in 20 days? Is actually a prerequisite chain. So a prerequisite chain stops us from completing the tasks earlier. So what are some examples of prerequisite chain from our little example here? So one prerequisite chain would be something like BCE. So BCE. So it's a prerequisite chain because first I have to complete B, and only after that can I start C, and only after that can I start E. So how long does this prerequisite chain take? Well, B took 3, C took 1, and E took 3. So B took 3, C took 1, and E took 3. And so in total, this prerequisite chain took 7 to complete. So that means that we can't complete all the tasks in earlier than 7 time steps. But there might be a yet longer prerequisite chain that stops us from completing it even before 7. So maybe we need more than 7 because there's some other prerequisite chain that we haven't looked at. So what's another prerequisite chain here? So here's another one, maybe ACE. And let's see what number that prerequisite chain is giving us. So A is 1, C is 1, and E is 3. A is 1, C is 1, and E is 3. So in total, this is giving us a 5. And so this prerequisite chain is telling us we cannot complete all the tasks in earlier than 5. But the basic idea is that the longest prerequisite chain gives us the shortest completion time for all the tasks. So what we'd really like to do is somehow take a look at this graph and in it find the longest prerequisite chain. So we'd like to find the longest prerequisite chain. Because that's the thing that basically limits us from completing everything earlier. So let's see how to do that. So let's go back and take a look at our graph right here, which was our topological sort. Okay, so if we want to find the longest prerequisite chain, let's take a look at this chain BCE. So BCE, so right now there's kind of a completion time for every task, but on this chain right now we only have 2 edges. So we don't have enough edges to actually express all of these numbers if we're going to use sort of shortest paths to help us find this longest prerequisite chain. So to fix this problem, what we're going to do is we're going to add a start and end node. So start and end. So add a start and end node. And basically this start and end node, they kind of represent tasks that take 0 time. So start is a task that takes 0 time, that's a prerequisite to everything. and end is a task that takes 0 time that has everything as a prerequisite. So I have to complete everything before I can get to end. So add edges from start to all tasks. And in fact, you don't have to do all tasks. You could even just do or all tasks with no prerequisites. Because it's really these tasks with no prerequisites that can be the starting point of our execution. So here are the edges we're going to add from start to the two tasks that have no prerequisites, which are B and A. And similarly, we're going to add edges from each task to end. And you don't really have to do each task to end. You can do each task that is final. And by what I mean by final is it has no successors. So just abbreviating successors here. So the two edges that we're going to add is from D and E to N, because those are the two tasks that have no successors. So now we've constructed this graph with the fake start and end node. And now we have a decision about where to put our various costs. So we can either pay for task B on the way into node B or on the way out. And this is going to have a different meaning. So if I pay for node B on the way in, then this node is going to denote the finishing time of task B. And if I pay for node B on the way out, then the node denotes the start time for task B, because of course I'm paying after I leave the node. So let's just have these be finishing time. So let's pay on the way in. So that means that the cost of B has to go on all of these arcs that are going into B. So the cost of B was 3. And so this should get a 3. The cost of A was 1, so everything going into A gets a cost of 1. The cost of going into C is whatever the cost of C was, which was 1. So this one gets a 1, and this one gets a 1, because that's the cost of going into C. Then the length of task D was 2, so that makes this edge be a 2 and this one also be a 2. And then finally, 3 had a cost of, or E had a cost of 3, so this edge going into 3 has a cost of 3. And the two edges going into end have cost 0 because we don't have to pay anything for end. That was just a fake node that we added for the purposes of modeling. So this is our graph now. And now a path from start to end kind of corresponds to a prerequisite chain, and the length of that path corresponds to how much that prerequisite chain is slowing us down. So if we look at this path BCE, it's start to B, that's a 3, then B to C, that's a 1, and then C to E, that's a 3. So that's giving us that total cost of 7 that we had before. So 3 plus 1 plus 3 gave us that 7. So we want now the longest path from start to end in here. So we want the longest path from start to end, because that longest path is going to give us the longest prerequisite chain, which then tells us the minimum amount of time in which to complete everything. But the problem is we haven't really learned anything about longest path. The only thing that we know is how to solve shortest path. So let's see how we can try to solve this particular longest path problem with the shortest path. So let's just write down what the longest path problem might look like. So it would be something like maximize over y variables the sum of Cij, Yij, where the ij's are edges, subject to some constraints. So this is just saying find the longest path maybe from start to end. But we don't know how to do this. So what I'm going to do is just multiply this expression by 1. So here it is. I multiply it by 1. And since I multiplied it by 1, that didn't change anything, so this is just an equality. And now what I'm going to do is take this minus 1 and move it inside of the optimization operator. And so you should remember from previous classes that when we do this, when we're switching a minus 1 with this optimization operator, the optimization operator changes direction. So what we'd get here is minus 1 times now the minimum overall y's of the sum of minuscij's. So this is where this minus 1 that I'm moving in ended up, times yij's, subject to some constraints. And the reason that we did this is because this inner problem here now is just a regular old shortest path problem. Except now it has some negative edge lengths. So what this tells us is to find the longest path from start to end, we can find the shortest path where we change all of the lengths to be negative. So let's see how that shows up in our example. So let's take this graph that we had over here with all of its lengths. So we want to find the longest path from start to end over here. And the way that we're going to do that is we're going to make all of these lengths negative. And now we're going to find the shortest path from start to end. And so if that shortest path has a value of something like minus 7, then if the shortest path has a value of minus 7, then the longest path is going to have a length of 7. So we're going to be off by a minus sign when we do the shortest path because that minus sign gets taken care of this remaining minus 1 outside of the minimum. And so we want to find the shortest path in this graph with its negative edge lengths. So that's the basic application that motivates us. So now let's discuss an algorithm to find shortest paths in directed acyclic graphs with negative edge lengths. So let's discuss the DAG shortest path algorithm, which takes as input a graph G and a start node S. So remember that DAG stands for directed acyclic graph. And since the graph is acyclic, it means it cannot have any negative length cycles, so shortest path works perfectly fine, even if some of the lengths of the edges happen to be negative. So here's the idea behind this algorithm. So the first thing that we're going to do is topologically sort G. The next thing that we're going to do is we're going to set these distance labels from S to every other node to infinity. So we're guessing that every node at the beginning is just infinity away from S. Then we're going to set the distance label from S to itself to 0 because we know that S is 0 away from itself. And the final thing that we're going to do at the initially is we're going to convert G so that predecessors is easy. And now we're going to enter the main loop. And the main loop is just process the nodes left to right. Let's say that the current node that we're processing is V. And what we're going to do is basically look at the predecessors of V and let U be the predecessor of V. That gives smallest dsu plus cuv. So this expression should be quite familiar. So we're looking at predecessors of v, and we're saying which is the one that's giving us the smallest distance to v, because that's the distance from s to u, and then that's the last edge. And so the predecessor that's giving us the smallest value over here must be the predecessor through which the shortest path is going through. And let's call this value L. So that's just a shorthand for that expression up there, so we don't have to rewrite it. So we have this predecessor that's giving us the shortest value, and then the next thing we're going to do is if L is less than the current label on V, which is going to be infinity because that's how we started pretty much all of the nodes, then we're just going to set the distance from S to V equal to L, and we're going to set the search parent of V to U. Otherwise, if L is infinity or V has no predecessors, if V has no predecessors or its L is infinity, then we're going to set the distance from S to V equal to whatever the label was, and we're going to set the search parent of V to none. So this basically means that there is no path from S to V, because all of the predecessors are giving us infinities in terms of the path through them, or V has no predecessors, which means that there must not be a path. So our infinity label on V is just going to stay, and its search parent is just going to be none. So let's run this algorithm on this example graph, because I think that running it is actually going to help us understand it better than just simply talking about the pseudocode here. So just seeing a couple of examples I think is going to make this algorithm very clear. Okay, so here's our graph, and the first thing that we have to do is start with some infinite distance labels. So start is going to get an infinity, B gets an infinity, A gets an infinity, C gets an infinity, D gets an infinity, E gets an infinity, and N gets an infinity. Except at the beginning, since start is our start node, it's going to get a distance label of 0. And so now we're going to process the nodes left to right. So we're going to process the nodes left to right. So let's begin with start. So start has no predecessors, and so that means whatever its distance label was before is just going to remain. So that's why we fixed the 0. Then we're going to process the next node on the left. So this node has only one predecessor, which is start. And from that predecessor, we're getting a value of 0 and then a -3. And that's the smallest one. And it's smaller than infinity, so that's going to become a -3. And so this thing gets set to -3. The distance from start to B is -3. So now let's do A. A only has one predecessor, which was start. And that predecessor is giving us a value of -1. So this gets fixed to -1. So now let's do node C. It has two predecessors. So from A, we're getting a value of -2. And from B, we're getting a value of -4, which is this -1 plus this -3. The -4 is the smaller of the two. And so that's the one that's going to go in here. So that's -4 for C. Let's do D. It has also two predecessors, C and A. So from C we're getting a -4, -2, which is a -6. And from A we're getting a -1, -2, which is a -3. So the -6 wins out. So -6 right here. So let's do E. E has only one predecessor, which is C. And C had a -4 plus this -3, so that's a -7. So this thing becomes a -7. And then finally, here is end. It has two predecessors, just E and D. So from E we're getting a -7. From D we're getting a -6. And so the -7 is the smaller of the two. So we get a -7. And that's our answer for the length of the shortest path from start to end. So that was basically an example of running DAG shortest path on this particular graph. But going back to what's the shortest amount of time to complete all of the tasks, the answer now is 7, because that's how long is the length of the longest path in the original graph from start to end, or -7 is the length of the shortest path in this graph where we changed all the lengths to be negative. So the shortest completion time for everything is 7. But somebody could come along and ask you a few other questions. So for example, they could ask you, what's the earliest time to complete task C? So to answer this question, we'd need the longest prerequisite chain from start to C. But we already have that right here. So we know that the earliest completion time for task C is 4. So similarly, the earliest completion time for task D would be 6, and the earliest completion time for task E would be 7. But people might come along and ask a few other questions. So maybe I don't want the earliest completion time, but what if I want the earliest start time? So what if we want the earliest start time? Let's say for task D. How can we find that from here? Well, I know that the earliest completion time is 6, and task D takes 2, so the answer would be 4. So that's one way to do it, is just look at the completion time. And subtract the length of D. That would be perfectly fine. But another way to answer this question is to just pay for tasks on the way out. So what I mean here is we can construct our graph, and before, when we had an edge, let's say A to C, when we had this edge A to C, we put the cost of C right here. But right here, we could be paying for tasks on the way out, so here would be the cost of A. So now this node A corresponds to starting task A. Whereas in our original graph up at the top here, the nodes corresponded to ending the task because we're paying for the task before we get to the node. And so if you run the analysis on this graph where you're paying for the task on the way out, then the label on this node is going to be the earliest start time for the task. So that's another way to get things. But yet a third kind of related question over here would be, what's the longest amount of time to procrastinate? So in other words, let's say that I want to finish all tasks by day 65, let's say. the question is, or the question that somebody could pose to us is, what is the latest start time for task D? So if I start task D too late, that's not going to allow me to finish by day 65. So the question is, what's the latest I can start task D and still finish at 65? So the idea here is the following. So we have our end and start nodes, and we have all of our tasks in between here, and here is maybe task D. So to find the latest start time for task D, what we need is the longest prerequisite chain here. Because it's that longest prerequisite chain that is going to tell us how much earlier than day 65 we have to start task D. And so the way that you can do that is just make the graph edges kind of point in this direction. So it's basically reversing the graph edges. And then just find the shortest path from N to D. Where, again, the costs are going to be those negative costs. And so that's going to give you the longest prerequisite chain. And that's going to tell you what's the latest that you could start task D. So one thing to remember here is you have to account for getting D completed. So that should tell you on which side you need to put the costs here. But that's the basic idea of answering this other question about the longest time to procrastinate before starting something. Okay, so now you kind of understand the basic ins and outs of this PERT CPM. But one last thing I want to add about it is what CPM stands for. So CPM stands for Critical Path Method. So the critical path is exactly the longest prerequisite chain. It's that chain that's stopping us from completing all the tasks earlier. So if somebody tells you, here's a list of tasks, I want to get them done really fast, what's the critical path? What they're really asking you for is what's this longest prerequisite chain? And you know how to identify it now because you could just go back and sort of run shortest path from start to end. And where that shortest path actually is giving you the critical path. So by the way, let's see how we can find that shortest path in this example. So in the pseudocode, we sort of talked about maintaining some search parents. But I didn't really maintain them when I ran this. But that doesn't prevent us from constructing the shortest path. So the way that we can construct the shortest path is just figure out from which node did this -7 come from. So the -7 came from predecessor E and not from predecessor D. So that means that this edge right here must have been the last edge on the shortest path. So then where did the -7 from E come from? Well, there was only one edge going into E, so it must have been on this edge that the -7 came from. So then where did the -4 come from? Well, let's see. From A we had a -2, and from B we had a -4, so it must have been from B. And then finally, where did the -3 from B come from? Well, it must have been from the only edge that came into B. And so these highlighted edges here are giving us the critical path from start to end. So it really turned out that this was the prerequisite chain that slowed us down the most, which was getting B done before C before E. And that's the path that had a total length of -7. So that's how you can identify the critical path from running things. So let's do a couple of more discussions here. So going back to the algorithm, so what's the runtime of DAG shortest path? So let's go back and try to evaluate this. So here was our pseudocode for our algorithm. So topologically sorting G, well, that just takes O of n plus m time. Setting some distance labels to infinity, that just takes O of n time because there's one distance label for every node. This is just O of 1 for setting the distance label on S. Converting G so that predecessors is easy. If somebody gives us G in a sparse format, this just takes O of n plus m time. And now let's think about this whole loop and how long that takes. So that was O of the number of nodes times the work per node plus the number of edges times the work per edge. So how much work did we have to do for each node? Well, for each node, we had to figure out what its label was and set its label. So that was O of 1. And for each edge, as we were running this example, we had to figure out what number that edge was contributing to A. So for example, let's say we looked at this node C. For each of the edges coming into C, we had to see, well, this edge is giving us a -2. Well, this top edge is giving us a -4, and the minimum of that is -4. So for each edge, we had to kind of compute what the value of the predecessor from that edge was. So that took O of 1 time. And so overall, this entire loop takes O of n plus m time. And so the algorithm overall, just when you add up all of these sequential steps, takes O of n plus m time. So this is a very, very fast algorithm. So its runtime is O of n plus m, while Dijkstra, if you remember, was O of n log n plus m log n if we implement everything with a priority queue. And so you can see that DAG shortest path is faster. And so whenever we're running a shortest path on a directed acyclic graph, it's actually better to use this DAG shortest path algorithm than it is to use Dijkstra's algorithm, because this DAG shortest path algorithm is just blazingly fast. Literally as fast as just reading the graph once, roughly, in terms of big O notation. So let's just do one more example of DAG shortest path, just to make sure that we all understand how to run it, and to point out that this algorithm works on any sort of directed acyclic graph. It could have positive edges, it could have negative edges, it could have anything. So here's an example. We can have any number of nodes here. And let's say this node is S right there, so that's the one we're going to start from. We can add some arbitrary directed acyclic graph edges. So maybe something like this. Let me add a few more here. So maybe that one, and that one, and sure, why not also this. And now we can put down any arbitrary numbers here. So 10, 12, -3, 7, 17, -8, 5, 6, -4, -10, let's say 9, and 3. Okay, so now we have lengths on all of these edges. So let's compute the shortest paths using DAG shortest path. So at the beginning, everything is going to get a distance label of infinity. So each of these nodes gets a distance label of infinity, except S, which is going to get a distance label of 0. So now we're going to process everything left to right. So this first node has no predecessors, so its distance label remains infinity. This next node, its one predecessor is giving us infinity plus 10, so that's an infinity, so its distance label is going to remain infinity. So this next node is S. Its predecessors are both giving us infinities, which are worse than the current label of 0, so its label is just going to stay at 0. The next node has only one predecessor, S, which is giving us a 0 plus a 17. So its label gets updated to a 17 and fixed to a 17. The next node has 3 predecessors, so let's see. From S, we're getting 0 plus a minus 8, so that's a minus 8. From this node, we're getting a 17 plus a 6, so that's a 23. And from this last node, we're getting a 7 plus an infinity, so an infinity. So the smallest of all of these is the minus 8 that we got from S. So this is going to just stay at minus 8. And so that's what its distance gets fixed to, because we've now looked at all the predecessors. So let's look at the next node. This one also has 3 predecessors. So from this predecessor, it's getting a 0 plus a 5, so that's a 5. From this predecessor, it's getting a minus 8 plus a 3, so that's a minus 5. So the minus 5 is winning right now. And from the last one, it's getting a minus 4 plus a 17. So here it's getting a 13. So the minus 5 wins out. And again, we got that minus 5 from this 3 plus this 8. So that was the minus 5. And then the last node here also has 3 predecessors. So from this guy, we're getting a minus 5 and a minus 10. So that's a minus 15. Over here, we're getting a minus 8 and a 9, which is a 1. And from the last one, we're getting a... so there isn't this last one because this one went to this node. We already counted that edge. So this only had 2 predecessors, one which was giving us a minus 15 and the other one which was giving us a 1. So here we get a minus 15. So let's see if we can reconstruct what the path was. If we had maintained search parents, we could do it, but we can also just backtrack. So the minus 15 came from this predecessor. So this must have been the last edge on the shortest path. The minus 5, where did that come from? Well, it came from this 3 and this minus 8. So this must have been the next edge on the shortest path. Where did this minus 8 come from? Well, it just came from this 0 and this minus 8. So that must have been the edge on the shortest path. So the shortest path from S to the last node over here is just these 3 edges, minus 8, 3, and minus 10, which give us the total length of minus 15. So that's just another example to show you that DAG shortest paths works on any directed acyclic graph, regardless if the edges are positive or negative. So thanks a lot for listening. That concludes class for today, and I'll see you all next time.